start with like the context for this stuff. Like this BEEFY gadget, which is what we'll talk about, exists in the context of bridges. So basically, the bridges are like some technology that will allow us to connect to different blockchains. And basically, by bridging, what we mean is that each blockchain should be able to verify the state of the other blockchain. So for example, if we have Polkadot and Ethereum, Polkadot should be able to know that the hash for block 5 is A, and should be able to verify that that is correct. I mean, not only the hash, but the whole header. And then the same for the other side. And basically, if we verify that the headers match on both sides, then we can build more abstractions on top of this to verify that the transactions um, that transactions are valid. And so basically, bridging has like two steps. The first step is to allow you to do actions on the other chain, so basically run transactions on the other side. But the way that we to be able to do to verify that those things happened, we need to verify the state of both blockchains. Yeah. So in order for us to do this, we will rely on this finality concept. Basically, the idea, this is more prevalent on like these new proof of stake chains that aren't using proof of work. And basically, the idea is that the protocol guarantees that after a given block X was finalized, it will never be reverted. And so we can trust that if we put some transaction in that block and that block is final, then we know for sure that it's going to stay that way forever. Like in proof of work chains or like in Bitcoin, this is like the confirmations. So on Bitcoin, you send some Bitcoin to someone, and if it's like a huge amount, then they advise you to wait for a couple of confirmations, because that if there were like 6 blocks built on top of your block, then it's essentially final. Like there's never, or it's very unlikely that there will be reorgs of Bitcoin that are longer than 6 blocks. But on Polkadot and like on these new proof of stake chains, we can do better than that, because we do have the concept of finality codified into the client itself. So once we figure out that something is finalized, the client itself will refuse to reorg to some other chain. So for example, in Polkadot, we follow the longest chain, but if some chain gets finalized, and we'll talk about how that happens in the next point, but if the chain is finalized, then, and if some other chain that's longer comes up, like the substrate client will refuse to reorg. Like what I mean is that the whole software, the whole blockchain client has a bunch of invariants that it respects regarding finality. And so this is great, because like once we know that a Polkadot block is finalized and we know for sure that it will stay there forever, then we can piggyback on this from like the Ethereum side, for example, if we are bridging to bridge these two chains. Like we know for sure that this is not going away, so we can find a way to verify that it is correct, and then we will know for sure that block X in Polkadot is hash whatever. So are we all on the same page so far? I mean, feel free to interrupt me, and I mean, if you have any questions, or it's fine. Okay, so the way that we finalize stuff in Polkadot is using this GRANDPA. So basically, GRANDPA is this protocol where the different nodes, the different validators, will be voting on what they think is the best chain, where our definition of best chain is like the longest chain. And once two-thirds of the validators, um, sign off on a given chain, then what we do is we find the common. I mean, so in short terms, we need two-thirds of people agreeing on something, and once they agree, that something is finalized. And the cool thing about GRANDPA is that they what we are coming to agreement on is the basically the prefix of the chain that everyone agrees on. So I have an image here that it's much better at explaining this than me. So everyone is voting on different things. So we in this example we have these three validators, and they're all voting on different blocks. Like we can assume that three forks happened. There's this fork which has the block D1. There's this fork which has D2 and then E2, and then there's this other fork which is F1. And these three nodes are on these different forks. From this guy point of view, the best block is D1. This one thinks that it's F1. This one thinks it's E2. So they'll each vote for these different blocks. And the cool thing about GRANDPA is that the protocol, what it will come to agreement on is the common ancestor for which two-thirds of them agree on. So I mean, it's two-thirds plus one. This is it's relevant in this example. So basically, two-thirds plus one in this scenario means that we'll need to have all the three validators agreeing on something. And so this guy votes for F1, this one for E2, D1, and what a protocol does is follows the blocks backwards until it finds some common ancestor that everyone agrees on. So this guy thinks that it's this block, this guy thinks it's this block, but as a whole, they all agree that C is legit. They do have some disagreements about what happens after C, but they all agree that C is you know is a canonical block. So this thing gets finalized here. Um, yeah, and so in short terms, this is basically GRANDPA. They're all voting for different chains, and then the protocol figures out that okay, let's finalize C because that's the only thing that we agree on. Let's imagine a scenario where we have another node here, like node 4, and let's say that E was voting for like G2, which was descending from this block. Like if we had that node that was voting here, then the finalized block would be D2, because we would have like 3 out of 4, like this guy, and this new guy that I'm making up. They would be voting for blocks that the common ancestor would have two-thirds threshold. Um, yeah. So what's different? What's different? And
Joe,
this. Yeah, yeah.
just out of
Go ahead.
curiosity, like if you have this example that you just showed and you add this
Yeah.
additional authority, what happens with the guy that was actually voting for D1?
Um, yeah. Basically, he will. You know, eventually, he will need to see D2. So this is kind of a convoluted scenario where his client didn't sync this chain. But yeah, at some point, either this guy syncs the D2 because it gets finalized, or he gets stuck here forever, because we finalize D2. So the next round, we will be finalizing something from this subchain for sure,
Okay, but since
right?
he already voted for D1, even if
Yeah.
he learns about D2, he can't really change his vote, right?
Oh, yeah, yeah, yeah. So yeah, his vote won't change. So he voted for D1, and he sticks to his vote. It's just a matter that he realizes that other people are voting for blocks that are further on, and he will just have to agree with them because he realizes that 2/3 of the people agree that this is final, so his opinion doesn't matter anymore.
Okay. Yeah. So
Um,
he's not wrong yet.
yeah,
He
exactly.
would be misbehaving if he signed D2 as well. But right now he's just, oh, sorry guys, I've made a mistake. I'm just gonna follow your chain, and
Yeah,
yeah.
actually, since this goes in two steps, so the grandpa, so this BFT agreement thing, um, you will see a lot of this word BFT agreement, because there's like a theoretical bound that says that you can only come to agreement with like 1/3 of dishonest validators. Like this is like a theoretical proof that you cannot get any better than this bound. And pretty much all of these protocols are doing roughly the same thing, which is like they do 2 rounds of voting. Like one round you pre-vote or pre-commit, and then on the second round, which is like an hint of everyone is saying I will do this, and you figure out what the others will do, and then you actually commit that change. So all of these BFT protocols, I mean, not all of them, but most of them, they come around to like there's this two-step process, like for example, like two-phase commits in databases. Like the
Mhm.
logic is still the same.
But for every
Okay.
round of voting, the number of validators is fixed, right?
Yes.
Because
Yeah.
otherwise you wouldn't know what would be 2/3.
Yeah. For sure. So at this point, let's just assume that the validator set is static and never changes. And which is true for a given period of blocks. So it's exactly like you said. We have what we call an epoch, or a validator set ID, which means that for this period of blocks, these are the validators and they won't change. And so yes, you know that if there are 100 validators, you know that you need to wait for 67 votes. Um,
So, quick question about the pre-vote and voting rounds. What happens if a malicious node votes differently between those two rounds?
that's a slashing condition. So I mean, no, it's so there are rules regarding what it can vote, uh, depending on what you pre-voted. So just to give some more context, the two phases in GRANDPA, they're called pre-vote and then pre-commit. The pre-vote phase is supposed to allow for everyone to come to an estimate of what can get finalized. And there's a voting rule that says that you can only pre-commit something that's the same that you pre-voted or lower. So if this guy pre-votes for D1, he can only pre-commit for like D1, C, B, but not for like D2 or something like that. So there are some voting rules that are required for this protocol to work and to keep its like consistency guarantees and blah blah blah. And if it doesn't follow those rules, then the vote is signed. The other validators can pick it up and post it on chain for like slashing conditions. That's you can just prove like, okay, this guy on pre-vote, I have a pre-vote signed by this guy on D1, and then I have a pre-commit from this same guy signed for D2. And since these things are signed, everyone else can verify that this is wrong and that it didn't follow the rules.
And the idea of this is that ideally you could come up with an as long of a as prefix as possible, right?
Yes. Yeah, that's the main benefit of GRANDPA, is that like it could go down for one day, and let's say that in a day we bake 1,000 blocks. After it comes back online, it doesn't have to finalize one by one. It can just, everyone agrees that the new best block is 2,000. They just vote on it and they just finalize the whole chain. yeah, that's the main advantage of GRANDPA. And in distributed systems, basically this is a trade-off, because this BFT stuff is a lot more a lot less efficient, because you need to be talking with like at least 2/3 of the people, right? So this scales, the communication of this stuff scales in like O(n) squared. Whereas when we are making blocks, for example, with proof of work or BAVE, let's just assume that BAVE is the same as proof of work. You don't need to talk with anyone, right? You're just mining the block. You find the valid nonce and you publish it to the network. Like, you don't need to ask for other people, should I bake this block? Do we all agree that I should bake this block? So it's the block production mechanism favors availability, whereas GRANDPA favors consistency. So for example, if half of the validators go offline, our block production will keep working. It's just that the block times will double, because half the people won't be baking blocks. But GRANDPA will stall completely, because we need 66% of people to agree. If 50% of them are online, then we can't agree on anything. Yeah, so there's other reasons why we need to have this separate consensus in Polkadot, but there's no point in going into that right now. Anyway, so the main thing of importance here is to understand that on GRANDPA, like, we are voting on chains and not voting on blocks. This brings a bunch of difficulties, which are the difficulties that we will address with BEEFY. So basically, the main thing is that not everyone is voting on the same thing. So yeah, let me just go through these types. So earlier I said that the bridges will be verifying each chain's state. Obviously, the way that we're going to do this is that this finality protocol produces some finality proofs. And what we want to do is, on each side of the bridge, we want to be able to verify these proofs, right? Because then if we have a proof saying that block 10 was finalized, if we can verify this proof trustlessly, then yeah, on the other side, we know what's happening on the Polkadot relay chain. The problem is that these GRANDPA finality proofs are, very cumbersome and inefficient to verify, mainly for two reasons. Not everyone is voting on the same thing. So it's not just a matter of looking at signatures, right? It's not like everyone, it's not like we are saying, is A the correct thing, and everyone is just signing something saying, yes, A is the correct thing. It's much more complicated than that. Like, they all are signing what they believe is the best block. And then, so we need to have the notion that we are signing blocks, and we need to have the notion of the ancestry of these blocks, right? Because these two people are voting on different things. All we see is the block hash that they say is the best, but we need to have the logic to figure out who their ancestors are to find the common ancestor. And so yeah, the finality proof for GRANDPA, we encoded in this justification type. So it contains the round number, a commit, and the votes ancestries. So yeah, this is just the round number. Like this, every time GRANDPA finalize something, it goes in rounds, like these rounds of voting, and they just have this number that's always incrementing. This votes ancestries is, let's look at this example again. So let's say that C, yeah, let's say that, yeah, these guys were each voting for their best block, and we figured out that C is finalized. So all we see is that C is finalized, the votes ancestries would contain like all of these chains of adders, right? So in this case, the longest chain would be F1, E1, D2, and C, because then you have this self-contained proof where, that proves that C is finalized. It contains the votes, these 3 votes, but in order to figure out, okay, this guy voted for F1, what does that mean? F1 is a descendant of E1, which is a descendant of D2, which is a descendant of C. So just to prove that C is finalized, you need to have all of these adders at end. And you need to have this logic for verifying the ancestry. And imagine that scenario. In normal cases, this shouldn't happen. There's no forks. Everyone is voting for the same thing. But we need to think about the worst case scenarios. Let's think about that scenario we were talking about earlier, where we go down for 1,000 blocks and then we come back online, and the proof might include 1,000 adders. And when we are bridging stuff, this will be running. For example, if we are bridging to Ethereum, this old logic will be running on a smart contract, which means that we will have some performance. Our environment where we will verify these things will be computationally limited. So this is just untractable. I mean, it would work for like 99% of the cases, but we don't want our bridge to just blow up in some edge case. These are the vote ancestries. So what is a commit? The commit includes the hash and the number of the thing that gets finalized, and it contains a vector of all of the pre-commits. And what are the pre-commits? It's some signed statement. We have some signature and some ID, like some authority did this, and it basically just contains the hash and the number. So basically, the pre-commits would be like D1. This guy, the pre-commit is D1. He signs it. He signs that. This one F1. Yeah, you get the idea. So what did I say here? Okay, so one of the problems is that, we cannot just rely on signatures. We need to have the data that's being signed, because it might be different. Like in our example, they're all voting on different things. So for example, we can't use stuff like BLS, signature aggregation, or stuff like that, because they're all signing different things. And we might need to attach, all of these adders to verify this stuff. And this was, in particular, like this BEEFY project, the scope right now is to bridge to the Ethereum blockchain. So it's just impossible that we would be verifying this in a smart contract. The gas costs would just be prohibitive. On top of that,
quick question on the commits and pre-commits. Would the target hash in the pre-commit and the commits typically be the same?
Yes. Like in normal scenarios, yes, because there's no forks. Everyone is voting on the same thing. Like what we vote on is actually what gets finalized. Like if you go into Polkadot right now, that's what's happening. Everyone is voting on like the same block 3, and that's what gets finalized. But in our example, that would not be the case. So the pre-commits would have like E1, the other would have F2, and the other would have G1 or whatever it was. But in the commit, what we have here is C, right? Because that's the common ancestor that got finalized.
Okay, gotcha.
Yeah, and so that's why we also put the adders in the proof, right? Because you will just need these adders to verify this proof. This is even more problematic when you realize that all of these forks are going away, right? Like right now we're finalizing C, On the next round, we might finalize, let's say, E1, in which case, like all of this data, okay, E1, yeah, the block E2 and D1, like they don't matter anymore. In a week, when someone syncs the chain, like no one will know about D1 or E2. They were just temporary forks that we finalized away. But for the justifications, we will still need to hold on to this data forever, because otherwise you cannot verify the signatures.
So
yeah, and so in the bridge environment, this is just yeah, wouldn't work.
So in Ethereum, these blocks could be included as uncles. Is it?
Yeah.
Do we have something similar for Babe as well? A side question.
So we added support for uncles, but then we are not using it. So there was this idea of like maybe with the same as in Ethereum, like rewarding these uncle blocks or whatever. But I think we're not doing any of that. I think we are not even. So I'm sure we are not rewarding them. I think we're not even collecting them. But yeah. But yeah, in Ethereum, maybe it could make sense to do that. Okay, so this this should answer like, why do we need another gadget? Why don't we just use GRANDPA? Like, these are the problems that we have if we want to use GRANDPA for bridging chains. I mean, this is a problem for Ethereum. Like, it's impossible to do it for Ethereum. Like, the gas costs wouldn't be worth it. But even for like substrate to substrate chains, which we already have code to bridge, these things still make it hard to implement, right? This is, I mean, this part about the ethers is still like the biggest issue with substrate to substrate bridges, I think. Yeah, okay. Another thing that we also needed to tackle for bridging blockchains is that, first of all, like, GRANDPA doesn't even guarantee that we will have finality proofs for each block. Because as we said, GRANDPA is finalizing, subchains. So in this scenario that we said that the chain was down for 100 blocks, when they come back, they will just vote for the latest one. So we will never have a finality proof for the intermediary blocks. We will just have an implicit proof. Like, if block 10 is finalized, implicitly, that block 5 is finalized as well, right? Because you wouldn't, like, as a validator, you wouldn't say, yeah, I agree that block 10 is fine, but the block 9, it's wrong, right? If block 9 was wrong, you wouldn't vote for that chain, period. So the point is that we don't want to be, bridging these proofs for every single block. Let's say that we do it every 5 blocks. So we pass on one of these proofs. On Ethereum side, we know that block 5 on the relay chain is the block with hash 0x42. 1 minute passes and we import another finality proof for block 10. So we can verify these 2 proofs independently and trustlessly that they are correct. But how do we know what the blocks 6 through 9 are, right? This would just be useless, because then someone wants to do something based on block 6 and you don't know what block 6 is, right? So the most, like, the easiest way to do this would be to just import all of the others to the other side. So you go to Ethereum and say block 5 is finalized, here's the proof, and here's the header for block 6, 7, 8, and 9. And then here's the proof for block 10. So you're basically replicating the blockchain from one side to the other. I mean, this is also not feasible, for the same constraints of verifying GRANDPA proofs. So this is where BEEFY comes in. These are the 2 problems that we want to tackle, like efficient block ancestry verification and you know, efficient finality proofs, which are not GRANDPA. Yeah, so we can think of BEEFY as these two components that will just tackle these two problems. The efficient block ancestry verification will be solved by using Merkle Mountain Ranges. So basically, let's just think about a Merkle tree. Let's say that we have a set of adders and a set of ashes, and we want to be able to create efficient proofs for set inclusion of a given ash. Yeah, we just put all of these ashes in the Merkle tree, and then we can just prove that something is part of this set just using log n data. This is just what we do in the rest of blockchain stuff. We use this for for the state, for example. All of the keys just exist in some Merkle tree, and then we use these Merkle proofs. And the only thing this Merkle Mountain Ranges, the only thing that the abstraction that we need to have is that they are just Merkle trees that have an append operation. So, every time we create a new block, we don't need to create this Merkle tree from scratch, because that would be just really inefficient. We would need to ash like all of these stuff, and then we have a new ash next block, and we will have to start all over again. So this just uses some neat tricks that allow us to accumulate new data into an already existing Merkle tree. So yeah, Tomek can go into more detail about this Merkle Mountain Ranges later on if we have more questions. But yeah, I think this is the abstraction that we need right now. We basically have this data structure where every time we get a new block, we can append its hash to this new structure, and then we can go to this structure and say, prove me that this block is part of the tree, and you just need log n data to create that proof. So this is much better than what we had before, right? Before it was just on, to prove that 6 was in the chain, you would have to send all of this data. So the first problem is solved for verifying ancestry verification. Then we need to tackle the GRANDPA finality proofs. And in order to do this, we will just create another BFT agreement round, totally separate from GRANDPA. So we will create this new protocol where, unlike GRANDPA, everyone will be voting on the same thing. It will just be like a more regular BFT consensus algorithm where we will say, do we all agree that block 10 is the block with ash A? And yeah, we wait to collect signatures. Once we have 2/3 signatures, that's finalized, and we move on. The tricky part here is that we will be voting on stuff that was already finalized by GRANDPA, and what we will sign is actually this MMR root thing. So the Merkle Mountain Ranges, just like the Merkle trees, they are trees, so they have a root, and from this root you can, this root encompasses all of the information that exists in the tree. So in this new BFT round, the thing that we will be signing on is what is the latest Merkle Mountain Range root. So yeah, let me think if yeah, do we have any questions about this?
So that means that BEEFY will have his own set of validators? Okay.
Yeah. So I mean, in practice, they are all of the same validators, because when you connect this to the staking stuff, like they they're all the same staking identities that were elected and blah blah blah. But from the code point of view, you it's like they are different authorities. Like they use different crypto, they use different keys, and from the point of view of Beefy, you just don't care. Like there's this set of validators, and you know who they are. You just wait for signatures from them. You verify them against the public keys, and blah blah blah. In practice, though, they are all tied to the same staking identities. They are the same people that are signing off in GRANDPA. They are the same people that are doing the blocks. It's all connected. But yeah, you are right that they are different. And like in this case, they will even be using different crypto schemes, because yeah, this is something that I say something about this, about the the crypto that we use in GRANDPA?
No.
Okay, so yeah, so this is another practical issue of GRANDPA. So the crypto that we use in GRANDPA for signing stuff is ETH 25519. And basically from the Ethereum side, from the EVM side, there's no what's called there's no built-in to verify this stuff. So this is also like prohibitively slow. Like we would have to do the signature verification implemented in Solidity. It's already expensive. This just makes it even more expensive.
You mean there's no precompile, right?
Yeah, precompile, yes, exactly. So one of the that's also one of the practical problems with using GRANDPA for bridging to Ethereum specifically. So for example, this is one of the points where Beefy will be using a different set of keys. We will be using I actually didn't put it here. Using ECDSA for easier Ethereum compatibility. So we will be using the same crypto that's used in Ethereum, because then from the smart contracts there's built-ins, there's what was it called? There's this compiled contract. Yeah, precompiled contracts that can verify this thing efficiently. So yeah, so this thing will be using completely different keys. In practice, though, for like the security analysis and making sure that the protocol is secure, the protocol is only committing on top of things that were already finalized by GRANDPA. So the way it works, yeah, I can explain this below. I have the step-by-step there. So this is so these are the two main reasons why we will be using Beefy. Those are the two key points that are part of our solution. So is there any question about this?
Can people misbehave in like their Beefy voting?
Yes. I mean, they could sign, for example, things from a competing fork. So for example, I'll just use this example because it's easier. Let's say that C, on this GRANDPA round, we finalized C, and in the meantime, okay, let me pick some other example. Okay, so let's assume that D2 is finalized, okay? And on the next Beefy round, you vote for this block. Like that's that's wrong. You shouldn't be voting for this. That's like a misbehavior. You're voting on something that wasn't finalized by GRANDPA. What else?
Are there any consequences though?
Yeah, you will get slashed. Basically.
Okay, so Beefy has like its own like slashing logic.
Yes. So actually, let me have that point here. Slashing. Because this is something that I actually haven't thought about yet. Like, what are the slashing conditions for this? I just came up with this one to give you an example. But yeah, this is a slashing condition. You're voting for something that wasn't finalized by GRANDPA. And basically, I think the way it will work, because this one will have to be interactive, because imagine, okay, this guy voted for D1 and everyone else knows that D1 wasn't finalized. How do you prove that, right? Like, you have to prove to the relay chain somehow that this guy misbehaved by voting on D1, so that the relay chain, slashes him, right? So I think that the way this will work is, yeah, I think this will be an interactive protocol where, let's say, this guy goes to the chain and says, on this round, on round X, this guy voted for D1, which is wrong. And I will put up a bounty of 50 dots or whatever. The value doesn't matter. What matters is that you'll have to commit to some amount of money for this. And then the chain gives, let's say, 100 blocks for this guy to come up and post on chain a justification that finalizes this block, right? And so if this guy is malicious, he won't find a justification for this block because it wasn't finalized, and he cannot forge one because that's the whole point of GRANDPA. And so either he posts something on chain which is wrong, and when the chain logic tries to verify it, it figures out that it's wrong and it slashes him, or it just doesn't reply to the contest, and after 100 blocks the chain says, well, he didn't come up, so we can just assume that he was malicious, and we'll slash him. And the other scenario where this guy is actually malicious and said that this guy voted wrong while he was voting right, then this guy will just come up and say, yeah, I voted for the one because it was final. Here's the proof. And then this guy gets slashed on like the deposit that he put up for for reporting that misbehavior. But as I said, none of these like slashing conditions are defined. We really didn't think about this yet. And this is something that I expect at some point we will discuss more closely with like Alistair, and we'll just have a list of conditions. When this happens, that's a slashing condition, and we will just implement that logic. But yeah, good point, because I didn't even write anything about it, and I didn't think about about it at all. Okay. So, what we have so far. So I split this thing into two main blocks. So the runtime code and the client code. From the runtime side, we have a Merkle Mountain Range pallet. So this is a pallet that implements that logic of that data structure that I talked about earlier. It allows you to push data into this Merkle Mountain Range. The routes are stored on chain. It does all its logic for correctly creating this tree, and then it has an API for like creating proofs of inclusion and verifying those proofs. Yeah, as I said, like this is Tomek did all of this stuff. I didn't work on this at all, so you will have a lot more to say about this. My understanding is that right now these are the main things that need to be done, like improving the API for generating these proofs, in particular, like some runtime API that can be called externally, like from the client side.
There is a pending PR to do that already.
Okay. Yeah. So this is like some detail, like implementation details of this Merkle Mountain Range. Like, unlike the Merkle trees, where you just need to store the root, in this Merkle Mountain Ranges, you will have like kind of like separate roots, which are like the peaks of the mountains. And these are the only nodes that you need to always have at the end. But right now we're storing everything on chain. And so the idea is that in the future, this data will be pruned and only exists on the client side to be able to like generate proofs and to vary and yeah, just to generate proofs. And then the runtime will only have the minimal nodes of the tree necessary to verify any proof. So that needs to be implemented as well.
So actually, to verify the proof, it's enough to have the root hash.
Okay.
But if you wanna append to the tree, you need this peak nodes as well.
Okay. Okay. Cool.
So the peak nodes are needed in the runtime to basically be able to grow the tree over time. But on the client side, it's totally fine to just have the MMR root, and this is why BEEFY is actually just kind of relaying the MMR root to the Ethereum chain, for instance.
Yeah. Because I suspect that like any proof will need to have all of the path all the way to the root, so it will include the peaks as well, or some peaks, I guess. I guess
exactly.
the proof is pretty much the same as a Merkle proof, right? It's
yes, like Merkle Mountain Range is this like you can always imagine this as a Merkle tree, but we are just able to add a bunch of nodes efficiently. Yeah. So the MMR proof is basically the same as a Merkle proof.
Yeah.
There's like a slight optimization being done, but yeah, that's irrelevant.
Yeah, I guess we are just like balancing the tree to make sure that this is like that we keep the log n bound or something like that, right?
Yes, because like the simplest way you can think about MMR is that you have a hash of the previous item, then you add a new item, you hash them together, and you have a new root hash, right? And you kind of keep growing this. It's not really a tree, it's actually a chain. Yeah, but the problem is that the recent stuff is like very efficient to prove, because you basically have two nodes. You just say, oh, here is the last item and here is the second last item, and this ends up being the root hash. But if you would like to prove something like a genesis block, then this is actually like on, right? Yeah. And the goal is to have a construct or a structure that allows you to efficiently prove recent stuff, but also not having like old stuff be the worst possible case. So we try to keep the old stuff in like log n range as well.
Yeah. Makes sense. Okay, and last time we talked about this last week, there are some low-level issues, like we are using an MMR implementation that already existed. And yeah, I remember last time Tomek was mentioning that there might be some low-level issues with how this dependency is actually constructing the tree. So yeah, we might also need to work on that, or just to re-implement it ourselves. I don't know. Yeah, so this is one side of the runtime. The other side is like the BEEFY pallet and the BEEFY primitives. So the pallet is very simple. It's just it's basically just maintaining the authorities. That's all it does. Like it integrates with the session module. The session module is the thing that will eventually integrate with the staking module. Um, you can think about it as like the module that will tell you who the authorities are. And this pallet is just doing that, like integrating with this module, figuring out, okay, these are the new authorities. I'll store it in my own storage, and I will put a digest on the logs to announce this change. We'll look at this code in just a bit. And the primitives are, yeah, basically just the types that that we will be using in this BEEFY protocol. So earlier, like we said, that we were going to sign the MMR roots. Like what exactly do we sign? Like this, yeah, it basically defines like these structs of, yeah, the data that you will be signing and that you will be exchanging back and forth. I mean, the critical part here is that we wanted to define this as soon as possible, because this is the stuff that Snowfork team. So the Snowfork team is this team that's working on the EVM side of integration. And yeah, these are the messages that they will be looking at. Like these are the messages that in their smart contract they will be getting. They will be extracting, verifying the signatures, extracting the MMR root from there. Yeah, so we wanted to define this as early as possible so that, yeah, we have some like shared vocabulary with them. Yeah, and we will also go through these primitives as we look at the client code. So any questions right now? So regarding the runtime stuff? Okay. Yeah. So from the client side, this is where we basically implement this voting protocol, right? This logic where we will be voting on the MMR roots. And so, yeah, we have like this working proof of concept of this BEEFY round logic. Actually, let me just see if this node example. Oh, shit. What's the name of this? Okay. Node template. Yeah, I will just show this working in a bit, but it will take like 2 minutes to compile. So basically what we do is, as I said, like we will be piggybacking on GRANDPA. So what the client is doing is it's listening to the GRANDPA finality notifications. Every time GRANDPA finalizes something new, we get a notification saying block X was finalized. And what BEEFY does is like GRANDPA, it works in like rounds. So every round we are trying to sign off on something, in this case, some MMR root. And the logic to figure out whether we should sign a given block is that we basically start a round for the next power of 2 block compared to the last one that BEEFY signed. So yeah, basically, if we are 1,000 blocks behind, then we will wait until 1,024 blocks, which is like the next power of 2, and we would vote for that block. Yeah, so basically this is just the rule where we are like implicitly synchronizing on, right? We want to have some common this is how we have some common ground about what the other people will be doing. And in particular, like we don't want to be signing on like every block because we just don't need that. Yeah, so after we figure out, okay, let's say that GRANDPA finalized block 10, and according to this rule, we were like, yeah, okay, we should start a BEEFY round on block 10. So what we do is we go into the runtime, we go into like this Merkle Mountain Range pallet, and we figure out what is the MMR root for that block, which we know will basically contain, this Merkle Mountain Range will contain all of the blocks that preceded it. So if it's block 10, it will contain blocks 0 to 10 to prove, not to 10, to 9, that we can prove ancestry of. So we fetch that root, we sign it, we create this BEEFY commitment. This is one of the primitives. So yeah, we basically create this message where the payload is just a signed MMR root, signed with ECDSA. We put out the block number, and we also put out the validator set ID. We can talk about the validator set ID later on when we are discussing the roadmap. For now, let's again just assume that the authorities are static, and so this is always 0. Yeah, so we create this thing, we gossip this thing around, and we just keep waiting until we get 2/3 more of this thing. Yeah, once we get that, then we know that the block is finalized according to BEEFY, like more than 2/3 of the other authorities agreed to sign off on this block, and we have our BEEFY finality proof, right, which is much more efficient, and which we can then pass on to like the Ethereum bridge, or we can use it to prove finality of the relay chain. Yeah, so essentially this is what the POC code is doing, and now we can actually look at the code and figure and find each of these steps in the code. So, questions?
Yep, I have a question. If you have a BEEFY commit for, let's say, block 5 to 10,
yeah,
and the Ethereum side wants to know whether there's a proof for, let's say, 7, is it agreeing to the implicit knowledge, or was it explicitly asking for 7?
So the way this would work with BEEFY would be, let's say that we, on Ethereum side, we will pass it BEEFY proofs for block 5 and block 10, okay? So it only knows about the finality of these 2 blocks, and we want to prove something in between. I, as a user, can tell you that block 7 is finalized because it is an ancestor of block 10, right? And how do I prove that it is an ancestor of block 10? With one of these Merkle Mountain Range proofs, right? So yeah, you know that if block 10 is finalized, all of the blocks that precede it are finalized as well. And now it's just a matter of proving the ancestry correctly. So yeah, that's how it will work. And in particular, because we won't be, so BEEFY won't be voting for every block. And even if it is, we won't be relaying like even if we have BEEFY commitments for every block, we won't relay them, all of them to Ethereum, because it's just wasteful, right? This thing is happening on Polkadot like every 6 seconds. So it's like twice the rate of blocks than Ethereum. And I don't even know how much gas this will cost to verify, but it would just be, wasteful. So you can, let's say that we do it like every 10 blocks. It's like every minute, from a user. I mean, I think it's also not going to be every 10 blocks. It's going to be more than that. But even if it was 10 blocks, from the user experience, it would be fine, right? It's just like you just wait 1 minute, and then you know that it's finalized. Yeah. Okay. So let's go into the code. So I will start by showing the pallet, because as I said, this is really a small amount of code. I don't know if you Andres, if you already looked at any of like runtime code. Okay, cool.
Yeah.
Cool.
Yeah.
Yeah, because it's not Rust. It's like
I'm familiar with that.
yeah, there's some of these macros that look a bit funny for people that are just starting. But yeah, all that we are doing here is we are storing what the current authorities are and what the next authorities will be. So this is the storage for the module. And then we have this trait that this is for like integration with the session module. So this is the thing that this will get called like eventually by the staking, like eventually, like at the end of the day, like in Polkadot, people will be staking dots to be validators. There will be elections, blah blah blah, and at some point there will be a new set of validators that will come through here, right? Like the session module will call this code to inform like BEEFY, like, okay, there's this method like on new session, and you get back an iterator of the new validators. So this account ID is like the staking identity, I think, and this authority ID is actually like the BEEFY keys that we'll be using. So yeah, the only thing that we are doing here is like when there's a new session, we just okay, here we are just mapping to get just the second side of the tuple, and then we call this change authorities function, which all it does is like it checks if they actually changed. If they did, because there might not be any changes, like from the no one new is taking, so the election just gives back the same result. So yeah, you just put this new value in storage, and we also do another thing, which is to put this digest in the header. This is just like an Ethereum log or an Ethereum event where this piece of data will be attached to the header. So someone that is just looking at the header, like a light client, can know that the authorities changed without actually like executing the block or looking into runtime storage or whatever. So this is all that this pallet is doing, just maintaining the authorities and announcing when they are changing.
Sorry, I just had a question about this optimization of the validator set change. So we don't trigger the digest item whenever the authorities don't change. But I started wondering, I was actually the one to implement that code, but I just started wondering now because we actually do have session keys there, right? So even though the validator set stays the same, the session keys are going to be different. So is there ever a case where this is not true, like that the session keys actually stay the same?
Yes, I mean in Polkadot people are rarely rotating their session keys, I think.
Oh, okay. I thought this is actually required to rotate the keys, but if it's
I don't think so. So okay. This will change at least every epoch, because even if people don't change their keys, not epoch. So at the end of every staking era, people will get rewarded. And so even if their keys don't change, this thing will come back. Okay, so in this scenario, no, it won't be different. What I meant to say is that here, this changed might come to true, even if this this iterator has the same elements, I think. Because I think that if when people are rewarded, we assume that the economics behind the given validator has changed, and so even though the keys are changed, the validator set changed. Yes, okay. Which means that maybe we shouldn't do this. Okay, yeah.
I guess we flag that as an area of further investigation.
Yeah. So actually, let me just put because now that I was thinking about this, like what I said, I was like showing, oh yeah, even though the keys don't change, we say that they changed because the economics behind them changed, but then we completely ignore it because we just look at the keys, and that's what we do for GRANDPA as well. And so now I'm thinking whether we should also do a set ID transition in that scenario. Just noted that to not forget it. But yeah, at least between sessions during the same era, they won't change. I mean, assuming that people don't change they don't rotate their keys, they won't change. Okay, so from the runtime side, like from the pallet side, this is it. I wasn't thinking of going into the MMR crate because I don't know if you think it's worth it, Tomek. Then we can do it afterwards. You can go into this crate and talk a bit about it. Otherwise, we move on to something else.
So I wouldn't mind looking into the MMR stuff offline, and
Okay.
once I have questions, I'll clarify that with Tommy.
Yeah. For now, we just care that it has an append function. Like, we don't even care about that. Like, it happens from the BEEFY point of view. This just happens. There's a root there which is populated correctly. That's all we need to know from the BEEFY side. You just need to know that you need to look at the storage entry, and that's it.
Yeah, to be honest, BEEFY doesn't even care what it's signing on, right? It's like
exactly.
it could be just arbitrary bytes because we leave it up for the like higher layers of the light client to actually interpret that data.
Yeah, exactly. Like, BEEFY is just signing something. It's only the Ethereum side will actually need to care about this stuff and figure out, this is actually a MMR root. I can use this to prove ancestry and blah blah blah. Okay, so this is the client side. What was I going to say next? The primitives. Yeah, we can look at these primitives. I mean, I think it's actually like a good idea to then come here and look at the comments, because there's also some extra information about why these things work this way. But yeah, basically here we are just defining the BEEFY crypto, which, as I said earlier, is ECDSA for compatibility with Ethereum. But a long-term goal is for BEEFY to be like pluggable in crypto. I mean, not only having pluggable crypto, like you could at compile time decide which crypto to use. I think that's already possible, but like being able to actually sign different things with different crypto, because the idea is that, imagine that tomorrow we want to bridge to, I don't know, Cosmos or whatever, that for which ECDSA isn't the best thing, and we want to use some other crypto. It would be cool if we could just use the same protocol and just sign different things, right? We sign ECDSA for Ethereum. We also sign the same thing with add 25519 for other substrate chains, because they can verify it efficiently. Yeah, but that's something that we don't need to think about right now, because right now we want to bridge to Ethereum. Yeah, so we're basically just defining all of the types that we're going to use. Like, what is the type of the MMR root hash? We know that it's a 25, 20 and 50. Oh Jesus, 256 bits hash. These are the things. So earlier I said that when we change the authorities, we put this event on the header. Yeah, these are the possible events. Like, we can announce that the authorities are going to change. We can announce that some authority was disabled. And we can also announce a new MMR root. This is just temporary stuff. Just in a bit, we will talk about, roadmap, one of the tasks. Yeah, so we also have these commitments. These are the messages that are actually being gossiped around, and this is what the Ethereum side will get from like when we relay information, when the bridge relays information from Polkadot to Ethereum, what they will get on the smart contract is a bunch of these commitments. Actually, we have another type for this. So yeah, we have this commitment where payload is anything, we don't care, but we know that it's an MMR root. We also have the signed commitment type, which is just a commitment, and we have a VAC of signatures. As you can see, this is already a difference. This is already much more efficient than GRANDPA, right? Because we can have just one commitment and a VAC of signatures, because we know that they all signed on the same thing. Yeah, so this is actually what, yeah, no, this is not what we will breach because we won't be bridging all the signatures. Later we will talk about that. And we have this witness thing. Yeah, so we, from the BEEFY client point of view, like the code that we are going to implement, this is all we care about, right? All we care about is creating these commitment messages, gossiping them, and signing them. We don't care about whether they're MMR roots. We don't care about verifying. It's not our job. Like, we are the relay chain. We know what is finalized. So then we have also this witness side, which are all of these types that we will use to create these proofs. So this is the stuff that will actually be relayed to the Ethereum side. So we have this signed commitment witness, where we have a commitment. We have a bit VAC. Right now it's a vector of booleans, which says that which authorities voted, because we only need 2/3 of them, so not all of them might have voted. And then we also create a Merkle root. We put all of these signatures that are here, like all of these signatures, we Merkleize them. Okay, so we put them on a Merkle tree, we get back a Merkle root, and we put it here. So, and this is what we will send to the Ethereum smart contract. So why don't we just send all of the signatures? This is just for like efficiency purposes. Like if we have 1,000 validators, then we just need to pass on like the commitment, which says the hash and the MMR root that's being finalized, just a couple of bytes of information. Here, if it's 1,000 validators, it's just 1,000 bytes of information. And then we create a Merkle root of all the actual signatures that we're not sending. And the way this will work is that then the smart contract will like interactively ask for these signatures, and will verify them against the Merkle root of all of the signatures that we have created. I mean, I don't want to go into details. I think this is explained here somewhere. But since we are signing off on stuff that was already previously finalized from GRANDPA, then we only actually need to verify 1/3 of the signatures. I don't remember, like, I would have to think again why this is the case, but we can also just trust Alistair. and yeah, this is why we are not sending all of the signatures. It's just like this more efficient dynamic protocol where the smart contract then will say, okay, then show me the signature for this validator, show me the signature for this one. And yeah, we'll have this interactive protocol for verifying the BEEFY commitments without actually having to send all of the signatures.
Yeah, I mean, it would be enough to verify 2/3 plus 1, right? But in this interactive kind of protocol, they have some analysis that says, yeah, it's actually fine to request even less, and we have almost the same guarantees.
Yeah, this is all about. Yeah, I mean, that's the reason why we are not using GRANDPA. It's just about making this stuff efficient, right? So the less data that we need to verify on Ethereum side and to transfer, the better. yeah, and so the rest of this file is just creating. Yeah, it's actually just allows us to, from an actual beefy commitment, allows us to create this signed commitment witness. So it basically is just Merkleizing all of the signatures, creating this bit vector, and then creating this type. And then we have some tests here, which the tests are also good because, like, if all that I'm saying now doesn't stick, when you go through these tests, it will, because they show. Okay, actually not these tests, but we have some tests for the light client. Yeah, it's here. So yeah, as I said, like if all of this stuff isn't sticking, then just start looking at these. Where are the tests that I'm talking about? That probably in mod. Okay, not the tests, but basically we have code here that shows our light client will use these beefy proofs. Like, this will be re-implemented as an Ethereum smart contract, but just reading this code will help you understand how this stuff is supposed to work. I mean, that's the reason. The reason why this exists was because, like, we were brainstorming in the beginning, coming up with the primitives, and this was a good way to, actually check that we were doing the correct things. So yeah, I mean, there's not much here. It's just like example code. I mean, what I mean to say is that this will not be part of what we are developing, right? Yeah, we will be developing like the runtime module and the beefy client to vote on stuff. Yeah. Okay, so from the runtime side, I think that's it. So now let's look at the client. So this is the something that I didn't show is that we have this we have this beefy gadget repo, and it's divided in like the pallet, which is where I showed like the authorities thing, primitives, the beefy gadget, which is what I'll show next, which is the client code that is actually implementing this gossiping and voting code. And then we have a node example, which is like this substrate node template with beefy on it. I mean, it's probably useless soon because there's already a PR open to also integrate this stuff into Polkadot. So yeah, soon enough we'll just be running a Polkadot node with like beefy to test it. Yeah, so now I will go into this beefy gadget thing. Okay, yeah, let me. Is this font size big enough, or?
For me, it's fine.
Okay.
I would do one bigger for the recording.
Okay. Yeah. Yeah. So as I said, let's just go to this walkthrough stuff. As I said, we start the way that this works is it's listening to finality notifications. So let's look at this gadget. Yeah, I don't even know. I think it's maybe easier to just start from the main and grow from there. I mean, it's not a lot of code anyway. This is like yeah, and there's a lot of boilerplate going on here. So this is our entry point to start the beefy gadget. This is just an async function that will just run forever. Yeah, this is just some code to initialize the gossip infrastructure that exists in Substrate. Then we figure out our local authority keys, if we have any. Like we go into the key store and verify if we have any keys for the existing authorities. Um, and then we pass on all of that information to this beefy worker. Yeah, and then we just call this run method and wait. Like this thing should just, yeah, it's a feature that should never return. It only returns an error because, it's just on the network and progressing, doing these beefy rounds. So let's look at the run method of the beefy worker. So we have this votes variable, and this is basically okay. This gossip engine is what we created earlier on the when we initialized. Yeah, this is something that's provided by Substrate, like the framework. And it's basically an abstraction that allows you to send messages on a given topic and then also subscribe to a given topic and get back messages, which will be our votes. So basically, yeah, this is all we are doing here. We are creating some stream of votes. Yeah, we're just doing messages for a given topic. Let's disregard the topic for now because this stuff is like yeah, it's like POC right now, and there's some tasks for this, and we'll talk about this later. So yeah, we just create a stream of vote messages where we get them from gossip. We try to decode them, and yeah, that's it. We get a stream of votes. And what the voter is doing is just running this loop where it processes one of two things, one of three things actually. Like either it gets a new vote from someone else, from one of the other validators, and in that case, it handles that vote. It runs the logic for keeping track of that vote. It might get a finality notification, which means that GRANDPA finalized a new block. In that case, we should start a new round. So this notification is like a struct that says that that says the hash and the block number of the new block that was finalized. And we also need to run the step, which is we basically need to poll this gossip engine future. So this gossip engine that we get from Substrate is a future, and we need to keep polling it so that it runs its logic. So that's all we are doing here. And if it ever resolves, then it means that there was an error. Like this is also another future that should never return unless there was an error. So let's look at each of these steps. So as I said, every time we get a new finality notification, we should start a new round. So let's look at this handle notification method. Handle finality notification. Yeah, we start by checking whether we should vote on this block or not. If we shouldn't, then we just don't do anything. Like the whole method is guarded by this if statement. And what is this should vote on? Yeah, it's basically that power of two rule that we have seen earlier. Yeah, it's just looking at the best finalized block, the best finalized block that BEEFY finalized, which is this. Yeah, so this is the best finalized block. So this is the best thing that GRANDPA finalized. This is the best thing that BEEFY finalized. So this one is always lower or equal to this one, for sure, right? Because we only start BEEFY after GRANDPA finalizes something. Yeah, so we run this rule, figure out the next power of two block that we should vote on. And if it's the same that just got finalized, then we vote on it. So this is the only thing that we are doing.
But
and
Note that there is an issue to change this rule a little bit, right? Because it's not complete. We still need to vote on at least one block in every epoch.
Yes, and we also need to cap this rule because it does the next power of 2, but if you are not lagging, then the next power of 2 is always like 1 or 2. So if things are all right, then you would be doing a round for every block, which is probably not what we want, because it's this is just a bunch of bandwidth that we will be using on the network. Okay, so if we should vote on this block, the first thing that we need to do is find the MMR root, right? Because this is what we will sign. So right now we are just assuming that it exists on the block. Like on the block header, there will be like this digest attached to it saying the MMR root. So this is one of the things that goes in the roadmap that needs to be changed. Yeah, it just goes into the header, gets the logs, and looks for one of these logs, like these MMR root logs. I mean, there's no point in looking at this because this will change. So first step, we get the MMR root somehow. Then we create a commitment. So this is, the payload is the MMR root. The block number is the block number that this is happening on, and the validator set ID is currently 0 because we are not dealing with like the validators changing. So yeah, we create this commitment, we sign it using the keys that we have in the key store. Note that where is shit? What? Okay. So this so there's I was looking for the place, like what happens when we don't have keys, right? Because we handle this in the beginning. Like we say that this local ID could be none. Yeah, and we handle it right here, like right away. So what we do is, if there's no local ID, we just return this pending future, which just we just wait forever. It's just a no op that keeps running forever. So right now, if you're not an authority, you're not running BEEFY, and this is something that will also need to change, right? Because if you're not an authority, you still want to run BEEFY, like you probably still want to get these messages so that you also gossip them to the rest of the network. You are just not voting. Anyway, we get back a signature. We update the best block that we voted on. We create this message, which is what will go on the network. It has the commitment, our ID, so that other people know who signed this message, and we have the signature. We pass it on to our gossip engine to gossip this message on this topic, and at this point, the other authorities will also magically start getting this message. And another thing that we do is that we call the code to handle the vote ourselves. Like if we had just received it from the network. So yeah, this is what happens when we finalize a new block. We basically just start this new round and gossip this message to the network. So let's look at the other side. What happens when we do get a vote? Then we get this handle vote message. So we have this data structure to keep track of the rounds. What is it? It's just a map that says that like the hash and the number, which is like the block that started this round, and it maps to some round tracker. And what is this round tracker? It's just a vector of IDs and signatures. So this round tracker yeah, it's just this vector with logic. Like you can add a vote to it, it verifies whether it contains or not, and it responds to the question of whether this round is done. And it is done if the length is higher than the threshold, which should be like 2/3. So if we have 10 authorities, the threshold here should be the number 7. This will return true whenever we got more or equal to seven votes. So when we get the vote, we just call this add vote logic, which returns a Boolean whether the vote was added or not. Apparently, we are not validating the signatures. Yeah, there's a to-do message here. Yeah, this add vote, yeah, it's just going into the map and adding the vote. Yeah, I mean, it's not validating anything at all. So here, the first step would be to validate the signature, verify that this is actually coming from an authority and that isn't just some random key signing something. Yeah, that logic doesn't exist. But let's assume that it existed and that the vote was valid and that it was added. So then after that, we need to figure out whether the round is done. If it is done, then we remove it from our data structure that's tracking the rounds. And we do this. Why do we do this? Okay. Yeah, so in the end, we are just creating, yeah, okay. So this is, if the round is done, then we get back a vector of the signatures, right? Which should have more than 2/3, which is actually the proof that this round is done. And then we create the signed commitment, which is the original commitment and the vector of signatures. In the future, we would persist this to disk. We are still working on extending Substrate to allow you to persist different proofs for different consensus engines. The issue is that GRANDPA is also, for a given block, storing these finality proofs. And right now we have no way of storing different proofs for the same block that refer to different consensus engines. Yoon is working on that, and he has a open pull request for that. Yeah, and so soon we should have support for this. Yeah, so right now we are not starting this on disk. This is a proof of concept. After you shut down the authorities, everything stops working pretty much. No state gets persisted. But we also have this this channel where we send the justifications. This is because then we have some RPC pub/sub where we can subscribe and get them in real time. Again, the reason we implemented that early on is because from the Snowfork side, basically they get something that works, that's finalizing. They have some RPC endpoint where they can subscribe and get proofs. It's just that the code that generates the proofs is like POC quality. If you restart it, it stops working. Obviously, it's not ready for production, but the APIs are kind of stable and allow them to move on with their work. Yeah, and that's all that we are doing here. Yeah, the round is done. We create the signed commitment, move on, conclude the round, and start with something else. Like eventually, GRANDPA will finalize something else, and we will start over. So let's see if this actually works. In the meantime, if you have questions, we can answer them. Okay. No templates. -t Alice. So yeah, hopefully this will work. So what I'll do now is just start a chain where, okay, let me enable like BEEFY trace where chain local. So I'll start a chain with like Alice and Bob, which are the two authorities, and we should be seeing like Grandpa finalizing something, and then after a bit, Beefy finalizing that same thing. Hopefully. Okay. So yeah, it's better to just generate some logs, and then we will look at them once they have what we're looking for.
So maybe in the meantime, you can go a bit over the roadmap. So as a kind of wrap up.
Yeah, yeah. So this is actually not working. It's not finalizing anything.
Doesn't matter. So I can look into that offline and come back to you with a question.
Yeah. Yeah. Oh, I think I am just. Is it because of?
Yeah, you have to validate.
I am not sure if it's just. I think minus minus Alice should imply validator, and they are authoring blocks. Anyway, we can check. We can check in a bit. So the issue right now is not so much with Beefy. It's just that Grandpa hasn't finalized anything.
Yeah, because in local you have 5 authorities and you only have 2.
Shit. Okay. So which chain does it only has like 2?
I don't know. Maybe dev chain.
Dev. Yeah. Okay. Yeah. Yeah. No, dev chain. I think it's just 1. Or no. Okay. So I think it's just 1, and yeah, here the thing that we want to see is already happening, even though it's just 1 authority. I mean, yeah, let's not waste time on this. It's probably just a matter of, yeah, if there's 5 authorities and we only run 2, it's 2 out of 5. We don't have threshold to finalize. So yeah, I think dev is just running with 1 authority, but we can look at what's happening here. So finality was at 0. Eventually, we got some finality notification saying that the block number 1 was finalized. So we ran this heuristic. Should we vote on block number 1? The difference is 0 to the previous block 1. The next power of 2 is 1. So the next block to vote on is block number 2. So we don't start a beefy round here. Later on, we get another finality notification saying that block 2 is now finalized. Our rule passes. So we send our commitment, right? This payload, this is the MMR root hash. Like if we went into the runtime storage at block 2, the MMR root should have this value. Yeah, and we just signed this statement. Here's a signature. We gossiped it. Eventually, we got this message as well. I mean, this scenario is stupid because, you know, it's just 1 authority. So immediately we just get this message and say that the round is concluded, and we create a signed commitment, and that's it. So if we were hooking up on the pub sub, then over WebSockets, we would be getting this notification in real time. And you know, when we have the whole thing done, like the relayers will be listening to that pub sub, getting these things, and sending some Ethereum transaction where they put this thing. I mean, not this thing, the other one, the witness thing where they don't put the signatures. But yeah, this is the entry point. Yeah, and it just kept doing that. So let's disregard. Let's assume that this would work with more validators as well. Um, okay, so do we have any questions for this? Otherwise, we can go into the roadmap. I mean, I realize that like 2 hours have gone by already. I hope it doesn't seem it went as fast for you as for me. Otherwise, yeah, I hope it wasn't boring.
Yeah, I think especially the all the context stuff and explaining the context and so on was extremely helpful for me.
Yeah, I can share this. I can export this to Markdown afterwards, and just we can put this on, I don't know, Notion or whatever. Um, so roadmap. So I put these tasks. I mean, as you've seen, like this code is just written in like prototype kind of fashion, right? Like it's really small so far. Uh, it's not verifying signatures or anything. Um, so I put these tasks in what I think would be a logical order to implement them, but it's it's not very thought through. So what I mean to say is these are just my ideas of what I think needs to be done. But we might do them in other order, and there might be more stuff than this that needs to be done first. So the first thing is that we need to handle validator set changes. We're not doing this at all right now. Yeah, as I said, we just assume that we are always have the same authorities, even though the pallet is putting these digests when the authorities change. We're not doing anything with that on the client code. So I think this is probably the first thing that we should tackle. Just allow supporting these validator set changes. Also putting some, this will bring some invariance into the code, like as Tomek was saying earlier. We want to make sure that we always have at least one commitment per validator set. So yeah, like if let's say that the authorities are the same for every 1,000 blocks. Yeah, we uh, in this period of 1,000 blocks, we need BEEFY to sign to finalize at least one block. Um, and I can actually go into detail why why we need that is because when the so let's say we have this concept of validator set ID that I alluded to earlier. This is just an incrementing number. We start at 0 or 1, and every time the authorities change, we increment this ID. And whenever a new validator set starts, we already know who the authorities for the next validator set will be. So from 0 to 10, let's say that the authorities are A and B, but okay, 0 is not a good scenario because it's an edge case, because it's a genesis. But yeah, any other epoch, we will know who the next authorities are. So if we finalized some block in this period, it means that the authorities for validator set 1 agreed on who are the authorities for validator set 2, right? This is how we are doing the handoff safely. Like the validator V1, they already know who the authorities for V2 are. And if they sign off on some block, it means that they agree on that. And so, yeah, this is how we will need one proof per epoch to do this safely. Because otherwise, if you don't verify it, let's imagine that you were skipping from set 1 to set 5, like in the middle, people could just make up. I could just say I am the authorities. It's this set of keys that I control, and if you don't verify them, and if you don't verify these transitions, then the proofs are correct because the signatures match, but the public keys shouldn't be those in the first place. So I think what we need to do here is that we will need to hook. I mean, there's a bunch of ways that we could do this, but I think this is the easiest one. which is that we hook into the import pipeline so that every time that a block is imported, we scrape this one of these signals. So where is it? So we import a block. Every time we import a block, we check to see if there's one of these digests there, right? And if there is, we know that BEEFY wants to change authorities. So we note this on the client side. Like we know, okay, there's this change has been announced, and now we just need to wait until we finalize something to actually change to this new authority set. And we already have code to do this in GRANDPA. So at least we can reuse this fork tree data structure, because the issue is that when this happens, when the block that contains this is authored, it's still not finalized. So imagine that you have a fork on the block that runs the elections. You could have two forks that are announcing two different sets of authorities, right? So what this means is that from the client side, we will need to track all of them. Like we will need to have this thing in some kind of tree structure where later on, let's say that we have block 10A and block 10B that say that BEEFY will change authorities, each to a different set. At some point in the future, GRANDPA will finalize one of these two forks, right? And if it finalizes the fork with the block 10A, then, you know, those we look into our data storage and we know, okay, so these are the actual BEEFY authorities. Does that make sense about this tree thing? So we have this fork tree data structure, which basically allows us to create this to keep track of these pending changes across different forks, and also it keeps track of like pending changes on the same fork. Because imagine that GRANDPA is down for a day, the validator sets will still rotate, right? Because Babe will still be authoring blocks, and every 1,000 blocks it will say, okay, these are the new BEEFY authorities, blah, blah, blah. But we won't be changing the authorities because GRANDPA is not finalizing, right? So we need to accumulate all of these things to, you know, first track which forks, which competing forks have competing authority set changes, and then for the same fork, which ones need to happen in order, right? Because as I said, if GRANDPA is done for a day, on Kusama that would be like 6 authority set changes. We need to make sure that we execute them one by one, and we can't go from set 1 to set 7 immediately.
But
André,
so sorry. With BEEFY, we can do something a little bit simpler. Like we don't really have to track all of the forks because we always piggyback on GRANDPA finality. So what we can do is we can just listen to finality notifications and then just go back a bunch of blocks to find if there was a validator set change.
Yeah.
So we don't really have to keep track of all the forks.
Yeah, for sure. So we can do that. The only downside is that then we require to have state available.
No, the authority set is in the header digest.
Oh, the headers, yes. Yeah, for sure, we can do that. Yeah. Yeah, we can just do that. So we can just piggyback on, you know, we know that if we couple this to GRANDPA completely, we know that if GRANDPA change authorities, then we should also change. And if GRANDPA says that they change on block 10, we can go to block 10, and we know that there will be one of these BEEFY digests there. So this is what Tomek is saying. And yeah, we can just start with that implementation because we know that this will be used with GRANDPA. Yeah, it's yeah, it's the so let's just disregard what I said here and start with that simpler implementation where we somehow get notifications that grandpa is changing authorities, and we know that if it changed, we also changed on the same block. So that's the first step. Yeah, we can write down that logic and then disregard this one. The next thing would be to actually have a proper round life cycle. You know, as you've seen in the code that we have right now, we're just running this rule blindly, and we always start a new round. So we have no logic for, okay, but what if we are already running 100 rounds? What if I concluded round 100, but round 2 is still running, which is useless at this point? So yeah, we need to have a better life cycle for these things. So for example, imagine that we are running round 2 and 5 in parallel. For some reason 2 is not finishing, but 5 finished, then we know that we can also stop running anything that's before that. Yeah, I mean that's about it. I don't know if Alistair has any other requirements on the round life cycle, but pretty much we want to make sure that everyone is synchronized on the rounds, like everyone is running mostly the same rounds, and we don't want to run, to keep running useless stuff. Yeah, that's it. And also related to this, although it should actually be its own point, when we restart the node, right now it has no, it just loses all of the information. So we will also need some mechanism to figure out what rounds the other people are in, right? So that when we restart the node, yeah, we just ask other nodes like which round they're at, or we can just again just piggyback on grandpa and figure out and assume that our grandpa rounds will synchronize eventually, so we will be seeing the same finalized blocks eventually, right? Yeah, I think that's the easiest thing to assume for now. Okay, another step. As I said, okay, so right now we assume that every header contains a digest saying the hash of the MMR root. This is a bit, it's just duplicating information because this MMR root already exists in storage, and it's unnecessary for every block to have this extra hash. So what we want to do is we want to listen to block import operations. And every time a new block is imported, we go into the runtime and fetch the latest MMR root hash. So basically, this will be using the pull request that Tomek said that he has open to create a runtime API for the Merkle roots, Merkle Mountain Range pallet. So basically, what the client will do is, okay, we imported block 10. The client goes into the runtime and goes and checks into storage what the MMR root is. Yeah, no worries. Yeah, the reason that we need to do this is because of state pruning. So this time I think I won't be contradicted by Tomek. In this case, assuming that we don't put the MMR root in the header digest and it only exists on the runtime, we need to do this preemptively because by the time that so this is happening in two steps, right? First we import the block, and then later on when grandpa finalizes it, we start a beefy round on it. Depending on this delay, it might be the case that at that point we don't have the state anymore. Like if we are running a node with state pruning activated, the state is actually pruned on finality. So by the time that block would be finalized by GRANDPA, we wouldn't be able to go and check the MMR root on state storage. What do I say here? Blah blah blah. Okay. I say here that we need to deal with forks, and I think we actually need to deal with them here because this is done at block import time, and GRANDPA hasn't intervened here. So yeah, what I say here, imagine that there's a fork at block 10. We will need to go into both block 10s, check the MMR root, and and start there. And then later on, GRANDPA will figure out which of the block 10 is actually the correct one, and then we can just drop that data from the client side. Another thing, as I said, we in Substrate we have some this gossip infrastructure that allows you to define a topic and then just get notifications for that topic. Right now, we are just using one global topic, which is just kind of stupid. If we go to the code here, there's this function topic that doesn't receive any argument and just says that the topic is beefy. So on this topic, you will be getting commitments from all of the rounds, which is, which is not inefficient. So, so if the latest round is 100 and there's some nodes that are slow and that are still processing round 90, everyone will be getting the same notifications, and we don't want this. So we want to create some logic where each round gets its own topic. Both of these, and also related to this, we want to make the gossip DDoS proof, because right now, this is another thing from our gossip engine thing. So when we create this gossip engine, I don't know if you noticed, you pass this thing, which we say allow all. Basically, this is a trait that we implement, which is this gossip validator. And yeah, but basically this is what we use so that the higher layer that's using gossip can inform the more like the networking layer of gossip to say, this message is useless, so just discard it, or this message is good, it's useful, so keep it and keep gossiping it to other people. And right now, the thing that we are doing is just implementing this allow all. So all of the stuff that we receive from gossip, it goes into this function, and we always say, yeah, process it and keep it, right? And this is not what we want to do, because this is, totally inefficient and it's DDoSable. Right now I can go into some node that's running Beefy, send it whatever kind of shitty data that I want. It will happily accept it and keep processing it. So here, both of these things are intertwined with one another, and both of these things will be heavily based on GRANDPA. So I can later on point to some GRANDPA code that does this same thing. For example, when we receive a gossip message, one of the first things that we want to do is make sure that the signature is valid, right? So that if someone sent us something where the signature is invalid, we don't even process it any further. And we also inform this to the gossip to say, this is invalid, so don't store it, don't gossip it to anyone else, and punish this peer, right? Because this peer sent us, shitty data. So what did I say here? Okay. So what I suggest is that we will need to exchange like small messages with our peers so that they know what our view of the protocol is. So pretty much which round we are in. So I send this small message, which is just an hash to my peer saying I am at round 10, or the round will be a block hash or whatever, but let's say that's a number. I'm at round 10, and since he is at round 5, he knows that whatever messages he gets for round 5, he won't send them to me because he knows that I'm at round 10. So I don't care about those messages. Yeah, so these two things, I assume that they will be implemented at the same time, because to make this thing efficient is also to make it DDoS proof. And yeah, this is what we're doing in GRANDPA. We exchange these small messages, which are called, we call them like the neighbor packets, which allow you to figure out, yeah, what's the state of this other node, to know whether you should send it messages, where you should get messages from him, from it, or not. Yeah, and at that point, since we know which round people are in, and we will have stuff into different topics, then what we would do is we wouldn't say to the gossip engine, send this specific message. We would just say, well, this guy is at round 5, send him the topic 5, right? Which is something that we can't do right now because we're grouping all of the messages under the same topic. Next point, yeah, is to, yeah, we need to add some logic to the pallet to be able to bootstrap BEEFY at any point. So yeah, I think this is not super, yeah, maybe this should be done last, I don't know. But the point is that BEEFY will be deployed eventually on Kusama and Polkadot, which are networks that are already running. So, the client code cannot assume that we are starting from Genesis, right? There should be, so we should have some way of noting BEEFY starts at block 5 million. And then the client code piggybacks on this logic. And my idea is that maybe we can even reuse the same logic to restart BEEFY if it's ever needed. So let's imagine some scenario where 1/3 of the authorities delete their private keys, and so you cannot finalize anything. So you cannot transition to the new set. You just get stuck forever. This is the same thing with GRANDPA. In this scenario, we will need to reset the gadget, obviously through governance. What I was thinking was that maybe this could just be like we update the block number where BEEFY started. So if we want to reset BEEFY at block 10 million, we just go here and say, BEEFY starts at block 10 million. But I didn't really think through about this. It's just a point that we do have to support this. Another point is sync with justifications. Again, I say here that I still need to think about this. Yeah, let's just ignore this part. So this is I'm basically saying, yeah, we need to verify all of these intermediary proofs. And then on this paragraph, I think I am just saying, yeah, let's just not verify the intermediary proofs. Let's just wait for GRANDPA to finalize things until the end. Once it is finalized, let's just go and figure out what the BEEFY set was then, and we can assume that it's correct. Because again, we can assume that if GRANDPA finalized block 10, that block 10 also included who the new BEEFY authorities are. So the only way where this is broken is if GRANDPA is broken. And the new one, which we just added, which is slashing, but this one I think we need to talk to research. Basically, when we had this introductory call with Alistair, yeah, we were just like, yeah, let's for now just assume that there's no. Let's just assume that the 2/3 are honest and move on with our life. Yeah, okay. I think that's it. So was that does that give you a good idea about what needs to be? I mean, obviously, I know that these tasks are very high level yet, but I think this should give an idea of what needs to be done.
Yeah, yeah, I think it's definitely super useful, especially since it's recorded and I can go back to it. It's basically kind of map the code to some of the higher level concepts.
Yeah, for sure.
Get an idea for what needs to be done in the future. So thanks a lot for your time.
Cool. So what I would suggest now is to read that, especially that thing that I showed about the test primitives light client, this thing, because I think reading this code will solidify all of how this thing will work in the end. Yeah, then I would just start looking at this at the client, and I think this validator set changes is probably what makes sense to do next.
Yeah, yeah. I think it's good to know to have some idea of what's the first thing to work on, and keep that in mind while looking at the code.
Yeah, for sure. Yeah, and I mean, we can then, it's what I want to say is that it's not like I gave this presentation and now I will go away. So any further questions or pull requests, I will be reviewing them, and any help that you need, you can just
yeah, we have our regular sync call anyways.
Yeah, for sure. Yeah. So what should we do? Anything else? I think it's been like 2 hours. I don't have water. It's like there's a Sahara desert in my mouth.
So we all can use a break now.
Yeah, I'm ready for lunch.
Yeah.
Yeah. So.
We may have lost Tomek.
Yeah, but at some point in time, we just will stop the recording.
Yeah, exactly.
Yeah, his hard drive will run out of space.
Yeah.
Exactly. Either he runs out of juice or the hard drive is.
Yeah. So my only question. So I need to convert this into Markdown, but I will post this on the Notion page somewhere.
Yeah.
And I guess
we do have one already. So in the bridges section of Notion, there's a BEEFY subsection.
Yeah. Okay. Then.
Or just put it in the BEEFY repo, right?
Okay.
I don't see any reason why it can't live there.
Yeah, or in the repo.
Yeah, works for me. And then if we want to duplicate it to Notion, we can do it.
Yeah.
And then what I would suggest is that, for example, let's say that we are going to start with this validator set changes task. Then we maybe create an issue for this in the repo where, for example, I'm not going to put this there because we said that we were going with the solution that Tomek suggested. Just of assuming that GRANDPA is correct. And so if GRANDPA says that the authorities are changing at block 10, then we just go into the database and get and look at the digest for that block. Yeah. But basically, what I mean to say is we create an issue for this stuff. We put like a basic description of what needs to be done there, and then we can discuss it there. It's just easier to synchronize like this. I think there's no. I think we shouldn't create issues for all of this stuff right away, because some of them are just very, like for example, these two are still a bit high level, and I guess we will still talk about them. And once we have a more clear picture, then we can create the issue. And
so if you take this one by one, that's totally fine.
Yeah. Okay. So I'll create a pull request to put this this document on the repo, and I will create an issue for this validator set. I think there's already an issue for it, so maybe it should be a matter of validator. No. Okay, I think we don't have any issue for it. Make sure the services work with no validators. What does this mean? Okay, this is if we are not a validator ourselves. Yeah, I think we don't have any issue for it. So, but we will just create one. Where are you guys? You're here. Okay, so
there's actually an issue number 15, which is get the client code to sign something, which is partially implemented, but it mentions tracking the validator set.
Okay.
Well, we can just rename it.
Yeah.
Yeah, I was actually lurking all the time, but or listening all the time, but in a different room. So.
Yeah, no worries. So yeah, let's. So no, it's not this one. You said 15.
15. Right?
Yeah. Okay. So yeah, let's just repurpose this this issue, I guess, and we can put there the description about waiting for GRANDPA to finalize some to change authorities, and then yeah, we just do that. So actually one of the first things that needs to be done, I don't think we have an easy way to get notifications from GRANDPA that the authorities are changing. So yeah, I will put this here in the issue. Let's just assume that you have a channel where you receive such notifications, and we will work on the GRANDPA side to add this. It's just a matter of putting the other side of the channel there and just sending the notification. Yeah. So yeah, I think that's it.
Okay. So
yeah, cool.
You can
Thanks so much, André.
Stop the recording now.
So we're all in the dark anyways. So
yeah. Yeah.
Okay. Thanks a lot for your time.
Yeah, no worries. Yeah. See. Nice talking to you.
Yep.
Yeah, and see you next week.
Yep.
In the meantime, if you have issues, just ping me on Riot, and that's it.
Good questions. Okay, great.
Okay. Bye.
Thanks. Bye, guys.
Thank you all. Bye.